the link is up there. So if you're on your phones, on your laptop, if you want to go ahead and put that down in case you do want to send any questions. As with most things, you never know how it's really going to work until it's live. So we'll see how it goes. Hopefully, you guys are putting up questions and voting and getting some great stuff out there, getting other people connected to. So why don't I introduce Dr. Omar Florez here. Get this good? All right, that's it. So Dr. Florez is a research scientist at the Visual Understanding team at Intel Research Labs here in Silicon Valley. He graduated from the Universidad Nacional de San Agustín in Peru. How's that? My Spanish?
Very good.
That's all right. Okay, it'll do. Thank you.
You have a Twitter
I'll
handle.
work on it. He's got everything. Dude's awesome.
What's the Twitter handle?
I don't have it.
See it. No worries.
He's too exclusive for a Twitter handle. That's what it is. He's a recipient of an innovation award by IBM Research, and his research interests are statistical machine learning, recommender systems, AI, and then he's really well published at ACM, IEEE, and House Journals. That's sort of the canned stuff. The cool stuff is he's been in your sheets. He's been a participant at BPDM before. He's come through the program. He's been mentored. He's made connections. He sat where you sat, and now he is not just doing really cool stuff in deep learning and advanced stuff at Intel, but he's also helping us organize this. Maybe even considering in the future taking over. Hint, hint. Yes, but yeah, he's incredibly accomplished, but also very smart and very talented, and really cares about this stuff. He does a ton of stuff with South Americans, Peruvians, and a lot of great work. So here he is, and he is going to give you a great talk. So there you go. Thank you.
And thank you for that kind introduction. Well, I wanted to start this talk first of all saying that it's a pleasure for me to be in front of so energetic, young, and also very talented with a lot of future audience. So as Caio said, I was there where you are sitting now. I was having a lot of big dreams, thinking who knows what will happen in the whole country. And I still have big dreams. I never stop dreaming. And so I just hope you also have big dreams. That's all about. Life is all about having good dreams. So I want to talk to you about this topic that I am quite passionate. I have been researching this for some years. It's an amazing topic, and I believe that many of the future of artificial intelligence and many of the things that we do right now will actually touch two important concepts, which are sensing and understanding. Remember these two words that I highlighted over here. We'll talk a lot about the slides. So usually people put demos in the end. I like to put demos in the beginning, so we can have an understanding, a common understanding of what's going on. So let me just run this demo, and I will talk to you a little bit about the concept behind that. So I envision a future where we will be able to communicate with computers in natural language, and not in the way that actually we are doing now, like searching, right? So let me see if I can run this because I don't see how the mouse. Okay, there we go. So this is we have two things here. We have an image. Many of you have a lot of information in your phone, for example. And we also have a user intention. Usually, we like to find ways to interact with our data. So it would be nice, for example, if I could actually interact in this way. For example, I can start asking questions to the computer, right? There is a smart algorithm behind, and I ask, where is this person? And they say, she's on the beach. I ask, what color is the umbrella? So the computer recognizes an umbrella in the picture, and telling me the color difference. Now I start asking to the computer, you know what, how many houses are in the picture? And you can see there are almost 3. Probably the first 2 are good enough to be able to count. So the computer is counting, the computer is understanding there is someone in the picture, the computer is understanding there is an object like an umbrella. Now it's asking and that could be a very suggestive answer, you know. However, the fact that the computer is doing many things together and providing an answer that is comparing to humans, I believe is amazing. And we'll see a lot of how this is happening. However, this is beyond object recognition, this is beyond face detection, this is beyond face identification. There is some level of understanding that actually we need to achieve in order to interact with computers naturally. In order to do that, we have to go to the basics. You know already the brain is an amazing machine, an amazing biological device. And there is something quite interesting about the brain. And there is some level of intelligence in the design. You realize that there are some areas like touch, right? Or the visual cortex. For some reason, the visual cortex is just behind your head. Who knows why that's the reason? However, other sensors like the hearing is really close to your ears. Or the smell is really close to your nose. I believe the reason why the visual cortex is right in the back part of your head is because there has to be many layers actually that information can process at the end, because vision is really hard problem. So of course that's just a theory. However, let me just use this as an agenda. We're going to talk about 4 different topics that are fundamental. The first one is the brain. We'll try to analyze at a very high level what is the brain. Then we'll try to understand if computers can sense. We'll talk about sensing. We'll talk later about learning, how computers can learn. And we will talk about the mathematics behind that, which are amazing. And then finally, we'll talk about the computer can understand. And that's finally the last one. So let me talk about the computer and also the brain. Let me compare probably the most sophisticated piece of hardware that we have at Intel, which is the Intel Xeon 5 CPU. It has around 60 cores, and if you compare with the brain has around 10 to 11 units. This amazing piece of hardware can make 10 to the 12 operations per second. But the brain can do 10 to the 16 operations per second. And in order to the brain to work at this level of power, it has to use 20 watts of power. And the brain is using 20 watts of power, and the CPU is using 240. So it's not only that the brain is more powerful, but it's also more efficient in terms of energy. And this is just a comparison to show you actually how far away are we from replicating what we have in our brains. And also, to be honest, we don't even understand how the brain works. We have some theories about that. But however, we have been trying to replicate some of the functionalities of the brain over time. So we have talked a little bit about the brain. Let's talk about sensing. And sensing happens at 2 levels. It could happen on hardware, or it could happen in software. Let's talk about the hardware. Many of you probably have realized already, but every single sensing capability that we have in a human body has tried to be replicated in hardware. For example, you have the balance, right? And the balance can be replicated, for example, with some gyroscope or accelerometers. And that's the reason why you turn your camera and then the picture automatically also turns with you. You have the speech and we have microspeakers. We have hearing sensors and we have microphones. We have smell and we have gas sensors. We have touching, and that's the way how you interact with your phone, right? You start touching your screen, and basically that kind of touching sensing that is implemented in hardware. So, and there are many companies trying to provide more and more sensors, as you can see here in this slide. So what is my point? My point is that somehow humans have been fascinated by sensing capabilities and have been trying to provide and implement that in hardware in order to make devices smarter. As you can see here, everything started in the year 2000. Nokia introduced the model S190. At that time, everybody was crazy. They said, why do you put a camera in the phone? It doesn't make any sense. The pictures are so crappy. However, as you saw in the previous slide, people have created a lot of sensors. So over time, they introduced more sensors. For example, the accelerometer in 2005. In 2007, the proximity sensor, such that every time somebody got a call, they put the phone next to the face, automatically screen the lock, right? Because there is a distance sensor, basically. And then there is the GPS in 2010. In 2015, something amazing happened. And I was very excited about that. Basically, Samsung introduced this phone, the Galaxy, and they introduced the heart rate sensor. So for the very first time, we are able to go, for example, from understanding what is your Twitter account, for example, or what pages a person was visiting, to go truly personal, to go, for example, to the level of understanding what is your heart rate. And if you put the wearables on top of this, you will realize that we are able to understand your skin temperature, for example, or how many steps you did, or how many hours you slept last night, or how well was your sleep, how long you stayed in the REM stage, which is associated to the largest period of rest during your sleep. So I believe these are amazing times because we are actually going from very high level information to very, very specific, truly personal. I believe the future is going to be like that. So how's going to be the future, actually? There's another point here. I don't know, but I believe they will have more sensors. We'll be able to understand the pollution around you. We're able to understand, for example, how well you sleep. We're able to understand what's affecting your productivity. We're able to understand what makes you stressful, what people around you makes you happy, and so on. So we will go from capabilities like detection, measurement, gesture monitoring, to some smarter, like sport performance, for example, or like understanding what is affecting you, or what's affecting certain relationships that you have in your life, or coaching you. How can you reduce your weight? How can you lose 10 kilos in 2 weeks? The computer will be able to tell you, knowing your sleep, your activity, your food, your pollution, how well you slept. It will tell you many things, and that will be great, and that will happen very soon. And probably will be So we have talking about the sensing in terms of hardware. Let's talk about the sensing in terms of software. So computers can listen and speak, and it turns out that they can listen, translate, and speak. And let me show you a video for that. This is an event from Microsoft Research in Asia, and basically they implement a system where spoken English can be translated into Chinese, into text, and text in English. This text in English is translated into text in Chinese, and the text in Chinese is translated into spoken Chinese. So it's an end-to-end system, very complex neural network, actually 2 neural networks, one doing the encoding from audio to text, then the sequence-to-sequence learning at a level of the text, and then the coding from text to audio. And that's really cool. Let me show you very quickly. Of course, I don't have audio. So let me see if I can activate the microphone.
I think you might be on mute.
Yeah. Let's see if this works. Really hard to plan everything.
The results are perfect. There are in fact quite a few errors. We're going to improve on later. There's much work to be done in this area. 在这方面有很多工作要做。But this technology is very promising. 用这个技术很有希望。
I think you got the idea. Now you can talk in Skype. Actually, that's implemented already in Skype. So you can talk to any friend you want, maybe a friend in China. You don't need a translator. You will have in real time. Language barrier could disappear in the future. Such a cool technique. Such a good application of learning.
Excuse me?
Yes.
From where this was presented?
It was presented a couple of years ago from Microsoft Research in Asia.
Because the YouTube captions
Mhm.
are very bad in comparison to the Agreed.
Yeah, I just took this video from YouTube.
Oh, okay.
So I think the quality is not good because somebody just recorded.
No, of course. I was talking about the caption, how they do it, because these seem to be super good, and the ones that you have in YouTube are very bad.
Okay. Got it. Christian?
Repeat the question.
That's a good question. Do you have a microphone?
Thank you. No, I was just asking from when that video was.
2 years ago.
Yeah. Thank you.
Let me keep on, unless there is another question. So let's talk about vision, right? And vision is probably one of the most exciting part of this movement. So computer can see. Can I ask who is the guy who said Abraham Lincoln? Who said Abraham Lincoln? How do you know? Have you seen this picture or this picture? But I asked you about this one.
Yeah, I've seen that.
Okay. So somehow there is a translation in your brain, right? This is a very low representation of this one. However, our brain is able to generalize over this low representation and associate a concept and even a name. And the reason why I put this is because this is the level of how computers can see. Computers can see images as a sequence of integers between 0 and 255 in 3 different channels. Computer can actually see this a set of numbers. And the reason why I show this slide is because I want to show you some of the things that computers can do right now. This is a video that was shown by the CEO of Mobileye, which is a company providing self-learning capability for Tesla. So he showed this amazing video, and I want to show you what is the state of the art of this video. So what you can see in green are the areas where the car can go. They call it green carpet. You can see different objects, and you can see how far are the objects with the numbers. You can see some signs and what the signs say, the state of the semaphore, what is the meaning of the signs that you have on the street, and also the direction where the car is going. So this is working, as far as I remember, I may be wrong, with 95% of accuracy. 95%. I mean, 91 is not good enough for this domain. You have a self-driving car, with 91 is not good enough. So they have literally like 400 people annotating every single image, every single video, in order to provide this level of capacity. And that's the reason why we have self-driving cars now, because they have reached this level of accuracy. And that's amazing. So we have talked about sensing, we have talked about how computers can understand, not understand, but can actually perceive the world. In the end of the day, a computer what it really wants is to use sensors in order to know what's happening around. And what's happening around is called the context. And we can get a context from speakers, from video, from accelerometer, from gyroscope, from text. And in the end of the day, those are just excuses in order to get more information from users. So now we're going to talk about my favorite part, which is the learning, the optimization, the mathematics. It's called optimization because in the end of the day, we really want to minimize a function. And that's usually the technique used for this type of systems. So does anyone in the audience know what is the stride 8 cortex? I have 10 more minutes, so I can wait. Nobody knows what it's actually cortex. I don't know what's actually cortex. But I found a paper that was talking about that and was really cool. So this paper was published in 1959. And for many people, this changed the game. Many people think this is the reason why we have a lot of emphasis in vision within deep learning. So this was a really amazing experiment. They took a cat, they introduced a metallic bar, in this one, across the brain of the cat. They induced electricity, a small level of electricity across the bar, the metallic bar, and they start showing an image in different levels of orientation. What they realized was something fascinating. They realized that the intensity of the electricity across the bar was corresponding to the orientation of that stimulus in front of the cat. What that means is that for the very first time, we have an evidence that the brain is doing something different at the level of electricity and the level of the way how neurons are interconnecting with respect to the physical world. And that totally changed the game. So we were one step ahead to understand how the brain was working. So in other words, and just to recap, different orientations of the stimulus in the physical world were associated to different levels of electricity. It was kind of a histogram or kind of a signature for a different objects that we were seeing in the physical world. I totally recommend you to read this paper. It's quite amazing, even though it was published some years ago, but this was the foundation of our field. So let's talk about neural networks. I guess you guys are familiar with neural networks. So let me introduce to a neural network. This is a neural network. This is a real neural network, right? You have the eyes, you have the retina right over here. Hopefully this cannot be seen, but the retina is right over here. There is a high-speed highway over here, which is called the optic nerve. And then you go all the way down to the LDM, and finally, if it gets into the visual cortex. So this is kind of a very like a pipeline where you have different steps, and in every step you have something like a specialization of operation, meaning that in some of the areas, as you can see here, are very complex. The distribution and interconnection of the neurons are really complex, and in other areas are quite simple, as you can see here. Again, it becomes complex again in the visual cortex. So what people realized after analyzing the brain this way was something interesting. They realized that in the visual cortex, it's not only that position where the neurons are in the brain, but also how in what level of depth they are. Meaning that the deeper they are, the less dense it becomes the connections, as you can see here. Very dense connection, very high connections. So it turns out that also the depth was important. And probably that's the reason why they call deep learning now. Who knows? But it turns out that neurons that are very close to the surface were really interconnected, meaning there were a lot of parallel operations happening and with a lot of redundancy. However, as we go deeper, probably it was not the case. So it turns out it looked like they are actually doing different things. However, they are all doing synapses, and a synapse is a transmission of information. And they realized something interesting about the synapses. They realized that right before the synapses, the intensity, the voltage was really quick, really intense, really sharp. And right after that, as you can see here, it was a very slow and smooth transition. And somebody said, you know what, I know a mathematical function that exactly like that, and it's called a signal function, which is basically 1/1 plus e to the minus wx plus t. And basically that intuition is that close to the center, we have a very high slope, almost 1, very high change. And when we get far away from the center, we have a value that is very small, almost constant. So that's exactly what's happening in the brain, in the synapses. We have very intense interaction for the synapses, and if we get far away in terms of time, this is very smooth. So the reason why I mentioned this slide is because every single thing that we have said now has been replicated into artificial neural networks, and let me show you how. First of all, stimulus. We made a connection between this image and the concept and the name. However, we said that that image is, in the end of the day, just a set of discrete values, right? This input is a vector, and this vector is associated to some weights. Basically, this circle basically is a neuron, only one. And this neuron is basically getting some input. And it's assigning a weight to every input, such that in the end of the day, we have a linear operation, the inner product between the weights and the input. There is a nonlinearity, which is in charge of taking this to a different space. So with that simple function that we just described, remember? So in the end of the day, we have a number that is the output of this neuron. And that's essentially what a neural network doing. It's trying to replicate a lot of these neurons into different stacks and different architectures. So what we just said here is exactly what is trying to happen here. So somehow we get inspired into biology and we turn this into a computational system. So since we're talking about neural networks and we're talking about deep learning, let's talk about the most popular architecture for deep learning, which is called convolutional neural networks, or ConNets. There are amazing ideas behind the ConNets. First of all, let me talk to you about the difference between deep learning and shallow learning. It's called deep learning because we have many layers. It's called shallow learning because they needed to come up with a name to differentiate from deep learning. So it's amazing how science works. The idea is that we have neurons. Remember, we have seen this circle before. We have input to the neuron, and we have a nonlinearity, and this nonlinearity is mapping this to a different embedding or a different space. They stack this into a column, and they call this a hidden layer. And it's called hidden layer because it's not in the input layer, and it's not the output layer, so it's a hidden layer. The input layer is connected to the input, the output layer is giving us the multinomial distributions over the different classes that we may have in a project. However, for convolutional neural networks, somebody knows, Jan LeCun basically said in his paper, why don't we arrange the images in 2 dimensions? I mean, why should we put one vector, one column vector for this? If actually the images are coming in 2 dimensions. So the neuron should be also related to 2 dimensions. And that was a fascinating idea because we realized that a neuron, like here, can be associated to some part of the image. And a different neuron can be associated to a different part. So there was a special relationship between the position of a neuron and also the position of the input. And let me give you another intuition about this. And by the way, this is a convolutional layer. There will be 3 components of a convolutional layer: max pooling and dropout, and we're going to talk to them very briefly about them. However, remember that the neurons were in this feature map, right here. And they were living in the same layer, in the same feature map. All of them are living in the same layer. However, we have 3 different feature maps. And all the neurons in the same feature map are learning different things in the image. However, we can actually have many of them in parallel. And each neuron will be learning the same thing, the same position, but with a different weight. Meaning we have like multiple views of the same part of the image, adding more power and more expressivity to the problem. That's called convolutional layer. Let's talk about a pooling layer. Somebody said, you know what if we have the output of this layer, right? We have this output in this layer. Why don't we take a function that is less sensitive to noise, less sensitive to rotation, less sensitive to the different levels of brightness that we have in that image? And they said, oh, well, I know a function, it's the max function. The max function usually is insensitive to those. So they said, okay, so if that's the case, let's take a neighborhood and take the maximum of them and assign a pixels. Such that if we have, for example, 2 by 2 neighborhood, the input will be reduced by 2. So from 32 by 32, we have 66 by 66. And this operation is called max pooling. Very simple, very intuitive, and very powerful, because it kind of gives us a representation that is less sensitive to noise, variation, rotation, and everything. And finally, the third trick to understand convolutional neural networks is the dropout. Srivastava, I think 2 or 3 years ago, came up with this idea. And he said, you know what, neural networks are so powerful that they are learning the noise in the input data. We should find a way to regularize the complexity of the network such that we can randomly assign we can randomly kill some of the edges, assigning a weight of 0, and such that the network is still learning, but it's having a more regularized version, a more like simplified version. So such that we will not learn too much noise in the data. And that was the reason why they come up with this dropout. They assign a probability to every edge, to every connection across neurons, and they kill it. And they have a simpler version of the network, as you can see here.
How do they pick what to kill?
Say again?
How do they pick what to kill?
Random chance, random probability, random sample, all about random. And that's a really good question because the technique they use for optimization is called stochastic gradient descent. And there is nothing as stochastic as a random sample. So it kind of came out with the idea that's compatible with that optimization. And talking about optimization, let's talk about first how does it look like, right? Let me show you very briefly an example. This is audio, and audio can be represented also as an image because we have a spectrum. And basically the spectrum are, in this case, 13 different frequency bands, and we have information of them over time, so any audio can be translated into an image. Feature maps, as you can see in red. Each of them are learning something different. And then we have this as the first convolutional layer. We have the dropout over here. And basically the dropout, as we talked before, is giving us a more like simplified version of the outputs. And then we have the max pooling here. Many of them are 0 because they are black, because they are in black color, because they are 0, and basically because randomly they will assign a value of 0. This is a very huge matrix because we have 100 by 128. So those are all the possible connections between 2 layers in a neural network. Usually this is the part of the network that takes more memory, and this is the part of the memory that takes more computational power. And that's the reason why people use, for example, a very strong hardware for this part. And then you can have the output layer, very cool stuff, 100 different audio files and 3 different classes. That's why we have 3 columns and 100 rows. And then if you want to know what is the class of an audio, for example, you want to know if the audio is happy, sad, or neutral, you just take that file, that row, and just pick that the highest distribution across the column. It's that simple. And then we're going to talk about the loss function, which is a central part of optimization. And I'm going to go to this part really quickly because there are some equations in math. Really hard to explain sometimes. So for me, the most intuitive way to talk about loss function is like associating that to errors. And an error is basically the difference between the actual value and the predicted value. So the predicted value is kind of the likelihood, kind of saying, you know, what is the probability of having a class given the network that was trained. So we have this difference, and then we have a surface. For different values that we are comparing, we will end up having a loss function. In this case, the loss function is convex. Sorry, it's convex because we have a minimum. And it turns out that many of the problems that we have in real life are also convex. And at the end of the day, what we really try to do is, given this error surface, we're gonna go and find the gradient or the slope. And the gradient is basically telling us what is the degree of change across the surface, across the error surface. And we like to stop in a position where this value is 0, because that will automatically be the maximum of that function, or the minimum of that function. And that's the reason we have to call a gradient descent when we train a neural network. Basically, we will have a very well-defined loss function, which is so simple. It's amazing. For example, this could be the face of a person that looks happy, and also the pixels associated to that. So it's so powerful because it's so simple. You can associate anything in the loss function, and then you can start doing optimization. So you will do like, as you can see here, the gradient, and the gradient will update the loss function. We'll do compute the first derivative with the loss function, and we'll use that value in order to update the weights of the neural network. So in reality, of course, we want to stay here in the low value, but in reality, there are many ways to do this. The most simple one is what I just showed you. I want you to look at the red point here. The red point is the stochastic gradient descent, and that's what I just showed you. And the other ones are different techniques to do the same. We're trying to find the minimum. So as you saw, the red point stayed there forever. They didn't find the minimum. Meaning that for this type of functions, there will be something like momentum instead of accelerated gradients, eta graph, eta delta, RMS drop. And there are variations of the stochastic gradient descent, but turns out that they are more powerful. However, they follow the same principle. We compute the first derivative of the loss function. We update the loss, for example, the weights of the neural network based on this optimization. And basically, we take the output of a layer in order to compute the first derivative with respect to the input. And then for doing that, basically, they came out with an algorithm called backpropagation. They have a forward step, which is basically a multiplication of matrices. And then they have the backward, which is exactly what I showed you. First derivative of the output with respect to the input. And it turns out that we have a lot of inputs in a neural network because every layer has an input. As you can see over here. Every layer has an input, every layer has an output. So it's massive. We're talking about millions of parameters in a neural network. And that's the beauty of this. Because the deeper it is, the higher capacity it has to learn any possible function. People call it universal approximators because of the complexity they can achieve. And we have ways to actually handle the complexity. So that's pretty much the optimization part. Sorry if it's a little bit dense, sometimes understand all these concepts together in a very short time. So let's talk about the next level. You have a question?
Yes, that's okay.
Sure.
Can you go back to the loss function?
Do you have a microphone? Microphone is coming to her.
I fear you're going to hear from me all day. It's dangerous to give me a mic. But anyway, can you run back to the loss function for a second? Yeah, so how does this connect to the 3 layers or stages that you talked about? Where in those 3 stages is this applied?
Sure. You see theta right here? Right here. Theta represents the parameters that we want to learn. Every single edge, every single connection between 2 neurons, between 2 circles, is a parameter we want to learn. And that's theta. Basically, we are computing the first derivative of the loss function, which is basically the output of the layer. The last, let me go.
Right, yeah. So if you go even further back I mean, you have the three different stages, so is the loss function applied equally in all of them? I mean, the dropout, obviously not as much. Or is it, like, is it just in all of them?
You can use if you want.
Sorry?
You can use if you want dropout or not. I mean, it's up to
Okay.
you. You can choose what technique to
So,
use.
right, but I mean in the sense that that loss function is applied at all three of the stages equally?
That's an amazing question. And that's something I forgot to tell. Thank you for your answer, for your question. The last layer is associated to the loss function. Basically, the last layer, as you can see, we have two outputs. And the outputs will be the predicted answer for the neural network. And we'll have labels associated to that last layer. So the last layer will be basically this comparison that we saw here. And once we have them, we
Then
will
you use
propagate.
back propagation.
Exactly.
Got it.
Exactly. That
Thanks
will
so
be
much
also
for
there.
clarifying.
No problem. No problem. That's an amazing question because that's a recursive process. And everything starts simple in the end, and then it starts becoming a little bit more complex, and we have more complexity in the neurons. Great question. Now let's talk about a topic that I'm researching now, and that's why I'm so excited to show you this. It's about understanding. We needed to talk about the first 2 or 3 steps before in order to reach the level of understanding. I will show you why it's a little bit different. So let me ask you a question first. I like those questions actually. Do the kids need attention? Can I ask somebody maybe in the first row? Can I ask you, do you think they need attention?
I always need attention.
In this image, specifically.
Probably.
Why?
It's like they're about to start fighting or something.
Exactly. So usually we use the faces, right? And we say, you know what, something is happening. However, a computer can see a face with someone in trouble. The other face is actually having a lot of fun. And the other face is, I don't care. So somehow there is a sort operation here. Meaning 1 sort 0 gives 1. So there has to be at least one face in trouble rather than require attention. That's probably the way a computer thinks. But what about the forces in the image, right? You have 2 people and they are kind of fighting, they are kind of going against each other. And the other one is saying, I don't care, let me imagine that. What about the images? What about the objects in the car? You can see, for example, a book. What is a book doing there? You can see the baby chair. And given the window, you can see that they are following a car. So the way how we think is like this. You know what? There are 3 kids. One of them is in trouble. They are in a small space that is a car. And they are with a seat belt. So it's very likely they need attention. Because there is a set of conditions that need to happen together in order for us to act. And that's how computers don't go to this level. Computer can recognize an object, can recognize a face, computer can recognize even the pose. They understand that they are sitting. But computers really have a lot of problems, and we'll reach this state at some point, but we'll start connecting all the dots. Let me ask you a question to another person. Maybe someone in the second row. You like to answer, you like to ask questions.
Don't look at me. Ask somebody else.
Okay,
I mean, yes, he is.
Let me ask you. Is this person stressed?
Yeah,
Why?
maybe.
Why?
He looks a little worried, maybe. It's
What
got that,
about
like, not clear at all.
Is he stressed?
Yes.
Yes.
Why?
Posture.
Say it again.
The body.
The body. What about now?
Yes.
Well,
There is no person, so you cannot be stressed. But what about environment?
it's stressful. Yeah,
Stressful.
stressful.
Exactly.
Too
Around.
many.
So as you realize, our answer actually depends on what are the clues that we have there. And we work in a very hierarchical way. We start seeing, for example, the face, and we say, you know what, the most important thing is the face. Even in our social relationships, we usually judge based on the face. And then we say the pose, and we say the pose can tell us something. They don't need to talk, we just see the pose. And then somebody said, you know what, this person has a calculator here. He must be doing some math. And there are a lot of papers on the table, so he must be stressed. And there is a soccer ball. What is a soccer ball doing there? It's soccer, right?
But isn't that priming? I mean, if you showed us this photo first, would we say that he was stressed? Maybe, maybe not.
Like you
That's
started with the one with the
I
face.
totally understand. I totally
Run the
agree with you. I
experiment.
mean, if I ask you, are you stressed? Probably you don't even know if you are stressed. It's really hard to understand human emotions. There is no agreement at all. That's why it's so hard. And that's why if we cannot even do it, how computers can make it, right? So probably the most important question for me is why there are two keywords. That's why I don't understand yet. But nevertheless, for a person, this represents stress. And computers cannot go to this level yet. They are trying, but they are not going to this level to understand this stress because there are many connections, there are many contextual variables, there are many things that are more important than each other. At the end of the day, and probably that's the key word, there is common sense here. If we want to teach computers to understand this, they should understand common sense. So the question is, how can we introduce common sense? And that's exactly my project here at Intel. I'm going to show you some of the things that we are doing. They're basically many of the concepts associated with that. So we have talked about sensing. We have talked at this level. How can we absorb information, for example, images given cameras? And there are many things related to sensing, for example, perception, 3D reconstruction, representation. You have radars like LIDAR in central cars. They are sensing the environment really quickly, right? To know what things are far away. Then you have recognition. And in recognition, you have categorization, classification, identification. It turns out that the machine learning community have made amazing project in this part. 95% of accuracy, come on, that's a lot. Facebook can recognize faces with 95% of accuracy. Humans can do it with 92. We are at a level of outperforming humans for some of those tasks. However, what I want to do, and I want to show you, is that the upper level understanding. But we'll have human-computer interaction, we'll have common sense reasoning, we'll have semantics, we'll have sense making. Things that computers are currently having a problem to actually model or actually understand. But that's exactly what I believe will be the next stage for machine learning. In other words, we understand the image. Here we understand this person, for example, what is the road in the image, what is the tree in the image, what is the person in the image. And at the other level, we understand if the person is safe. And we understand that safe because he has a helmet, and also he looks like he knows what he's doing. So those are the three levels that I'm talking about. So, and I believe one of the reasons why we cannot make this happen is because we have oversimplified the problem. Somebody took a decision some time ago that we should have an image and a label. And that label doesn't encode semantics. That label is basically telling a name, it's basically telling the name of an object, it's telling us a place. However, that relationship is not rich. And therefore, it's really hard for us to encode relationships that have more semantics. In other words, the label doesn't have semantics. Basically, it's a very simple match between the content, the pixels, and the label. However, it would be nice if the label would be a description rather than a label. It would be nice if somebody if I ask, for example, what's happening, they would not tell me that there is a hand or a face or a foot, but actually there is a person laying down, or there is a girl about 20 years with some jeans and a sunny day. But that's a very description of this image that just didn't notice. And that's exactly what we are trying to do. For example, we have this relationship that happens a lot nowadays. Human asking to devices, right? And as, for example, searching. You're typing something and you get an image on Facebook. However, what we're looking for is this other level when we have interaction or a conversation. When I ask, the computer answers. Or when the computer can tell me something, I can actually replicate. And we have a conversation or a dialogue. And that's what we are trying to do, and I believe that's the next step for machine learning. In order for that to happen, we need to start consolidating some of what we know so far. We'll have convolutional neural networks associating the image. We'll have LSTM, or recurrent neural networks, learning the temporal dependency between words in order to learn a question, for example, or a textual description. And then we learn them to combine together into another network. So we will be very creative, and we'll start actually trying to consolidate semi-supervised models, and also try to understand the different signals that we can actually get. For example, if we have a question, we're actually encoding the intuition of the person, the intention of the person. If we have images, we are understanding the context, the visual context, and also the content. So let me show you a final demo to end the presentation. Is Brand here? Okay. So it happened 2 years ago. Basically, there was a panel, and she was there in red. And we have another BPDM member kind of leading the discussion. So I just took this image. I wanted to show to her, but probably I will show her offline. But basically, I will ask questions about the image. For example, who is speaking? And the answer is a man. Basically, the guy can stand up. Another question is, what color is her dress? And the neural network is speaking brands and saying the dress is red. Next question is, what type of event is this? And the answer is, surprisingly, a wedding. And finally, the most important answer, where are they? I say in the restaurant. So I want to stop here just to kind of provide some reasoning about this, right? Why the neural network is thinking this is a restaurant?
Because there's a table.
Exactly. I think you got it.
It doesn't have enough panels in its training set.
You also got it. So first of all, we don't have enough data, right? We didn't train the network with computer science and conference pictures or something like that. But still, the network is able to understand there are people sitting there at a table. Honestly, in Peru, in my country, if we don't have this big table, this big kind of door, it will look like a restaurant, and we will probably crop this right part of the image. My point here is that the network is trying to do its best, but still, I think, trying to connect the right points. It's still trying to connect the people sitting, the cups, the glasses, I don't know, the big table, and all of those situations are actually, I would say for a kid, probably that could be even a valid answer, because a kid never went to a computer science conference. So that's basically the message that I wanted to give you, that we're at a level where the computer can start reasoning, start providing some information about the content. And that's really cool. So my last slide is basically the take-home messages that I want for you to take. The first one is about teaching computers to sense and understand. We have talked about two important concepts, sensing and understanding. We said that sensing can be implemented in hardware and in software. I showed a lot of evidence, and hopefully I convince you that we are really obsessed with trying to replicate the human senses into hardware. Mainly because we want user information, mainly because companies really know what's happening. Somebody asked me once, what did Google buy next before? I think it's quite obvious, right? I mean, Google knows what's happening around you. Having a device at home, they may also be able to know what's happening inside of the house. In the end of the day, it's about data. It's about knowing your activities. It's about knowing your context. It's about knowing where you are, with who you are, what are you doing, what is your mood stage, what is stress, what is your physical activity. It's all about your data. And there will be services and also technology based on that. And then we're talking about understanding too. I have shown you some initial steps that we're doing in my team to encode semantics to content, to encode the intention of the user expressing the question in order to be able to connect it to content. Why deep learning? This is a very deep question. Why deep learning? Basically, because there are a lot of interactions across multiple modalities like text, audio, images, that are really hard to understand if we don't have a very powerful combination of different parameters. We actually need to create new parameters. We also need to create new representations. And that's exactly what's happening with neural networks. And finally, there are multiple network architectures. Actually, this is a field that is changing so much. Every 2 months, there is a new paper. And that paper many times validates the previous one. So you really have to keep up with a lot of readings. You have to go to archive and really understand what's going on. Many of the things I have shown you are the basic, but there are things like zero-shot learning, one-shot learning, batch normalization, saddle points, and you really need to kind of keep it up with that. And you will realize that every time there are multiple architectures being proposed. What we have shown now is convolutional neural networks, the most popular, but there are regular neural networks, restricted open machine, the notion of encoders. They are useful for different things, and they're all amazing. So I really encourage you to pick one and probably start studying also. Probably you already did already anyways. And let's talk also the future of computing in the eyes of machine learning. And that's my personal take, and maybe totally wrong. I don't know if I'm an expert in this area. But I want to talk to you about the future, right? First of all, it will be about hardware. And we'll have more sensing capabilities. We will be able to sense different things and we'll start connecting the dots, and we'll start providing interpretations and coaching, understanding, very high level things. And we realize how computers are actually having problems to actually deal with this level of information. And finally, it will be in terms of software. We'll provide understanding, and we'll, in the end of the day, I believe the end goal will be to help people to take their decisions with their data. That's basically the message. And that's exactly what I wanted to show with you and share with you today. Thank you very much for your attention.
So I think we have some time for questions using this mic.
Hi, I'm just wondering how far this goes. I mean, so the machine learning can detect settings and tables and chairs and faces and that type of thing. What about the cultural context? How does that factor in? Is there different algorithms for a different social context of culture?
There are. That's a great question. First of all, the first thing that we learn in machine learning is that a model is as good as the data you provide to the model, right? If you have that information, you will be able to take advantage of that in order to model it. I am a very big fan of Bayesian networks. Bayesian networks are able to express very explicitly the context. You will have another variable, a latent variable, and you will put a distribution, you will put a prior value. You can even learn that distribution, and you will make sure another model, like neural network, will behave in a different way, given the value of that variable. For example, you realize you are in a Hispanic country, you update the prior of that variable, and that will lead to actually a different behavior in the neural network. So it's possible to do that, and people are actually looking for example, to understand the different relationships that you have in your data given some context. Usually that's a very popular way to encode context.
Excellent, thank you.
Any other questions?
So great talk, by the way. Half the stuff I had no idea, so especially bringing stuff that was really interesting. There were a couple key inflection points that took shallow nets to deep nets being really popular and reused a lot, right? I think one of them was the ability to do that on GPUs and really do a lot of computation. Are there any other sort of promising points that are going to be other inflection points that can take the number of operations really needed to take this to the next level, let's say closer to the brain, right? Is it more hardware, more software, more optimization, more distribution? What do you see as sort of the key promising areas that can really take this a leap forward?
Yeah, that's a good point, Kyle. First of all, I think we're at a point where we realize that the hardware is important, but also we sometimes are limited by hardware. Think about a self-driving car, right? A self-driving car running such expensive amount of operations, we need a lot of electricity. So if you want an electric car that is also a self-driving car, it will compromise the battery and therefore the computation. And many times we have to choose one over the other. Would it be nice if we actually use something like BPDM, for example, which is an approximation of, for example, a very programmable hardware. It's a CPU that you can actually program. You can actually change distribution along the logic that you have in the CPU. I think that's a very promising one. I mean, to use this type of technology in order to have something that you can code, you have a new algorithm, you can actually change the logic inside of the hardware, and you will be able to kind of encode the new algorithm. It will not take so much energy. That's a promising part. And many of the current research is related, for example, to compressed neural network. They realize that there are a lot of redundancy in the weights, such that it would be nice if we can actually compress the weights. We can actually compress the number of layers. They call low power deep learning. Basically, the idea is that how can we have the same accuracy with less number of parameters, and therefore it will take less energy. So there's also a lot of work in that area. And also what I just talked, right, the level of understanding. How can we make sure we combine different types of neural networks, each of them doing totally different things, science and engineering that they will ask more complex questions. They will be able to answer. I would say those are the three participants. Oh.
Uh-oh.
You do, Megan. I'm curious that you've probably seen the hype graph, the classic Wall Street Journal, like, this is the point of the maximum hype. It seems to me that we're not even yet at the point of maximum hype on deep learning. What's your take on that?
I agree with you. I think this is kind of a hype at some point. We are kind of getting it now. At some point, we'll realize the limits of that, like any technology, right? Usually, I like to see that curve every year. And actually, I choose my project or many of the papers I want to read based on that curve. For example, I think 2 years ago it was big data, right? And now it's actually getting down in the curve. So and now you realize, or some people realize that big data are in big companies. So not all the companies have big data. So what do you need to actually basically hardware and software? I think we'll touch eventually the limits of deep learning. We'll realize what can happen with deep learning, what can be done with deep learning. I believe we're not at that stage, and I'm very happy we're not at that stage, because we are actually being very creative about different architectures. And so far, there are a lot of innovation. I didn't see any other field, even in computer science, with so much change, with so much speed in terms of proposing new ideas, in terms of sharing the code, in terms of sharing the knowledge, in terms of being very open about the results, collaborating across companies. But that's what I like of this. I mean, the innovation is huge, it's so fast.
So you think there's more than just that?
Absolutely.
I told you, if nobody else asks, I'll keep talking, but that's why I said it's dangerous to give you the mic. Here we go.
Thanks.
Okay.
Liberating.
So going back to the man sitting at his desk, I was wondering, it depends on the priors of, for example, a crowdsourcing group. So let's say that we have a crowdsourcing group and they have certain cultural priors or whatever, then they may decide that he's either stressed or not. Maybe they know him personally and they know that he has a messy desk. So so the real question is, how do you account for priors that you want to avoid, like biases that the crowd shouldn't have and shouldn't be driving these kinds of decisions?
There is a magic word for that, and it's called agreement. Basically, you ask a question not to only one person. You ask for the label to not to only one worker in Amazon Mechanical Turk, but you ask that to 5 people, for example. And the more people you have to provide you a label that is biased with you. So that basically, especially if they are not connected, for example, with a person, you said, and especially if they come from different backgrounds, really hard to get that. And I believe there will be always bias, no matter what you do.
No, so my question is actually the other way. So the minority group is the one that has the correct information, but the majority group is the one that's driving the wrong outcomes.
Well, I don't agree with that. I believe that according to the simple theory, right? When you have more data, basically you converge to the right answer. So when you have more people, basically you are getting less bias, because you will kind of get to the mean value, to the average. Okay? So I don't agree with what you do.
All right, that's a good conversation to have offline, I think. But let's give a round of applause to Dr. Florez. So next, we are going to have.
Thank you, Omar. Okay, so I know we have a break somewhere